Welcome back, guys. So yeah, let's see this week. Let's continue where we left off. We are working on the file system layer, trying to integrate both the VFS high-level helpers with the ext front end. We do already have the working implementation of the backend layer, which is the block layer that is internally using Wedge.io to connect to the ext layer. So currently we just have to finish the VFS and the front end for Next. Overall, we're still trying to finish up our own kernel. We have good working setup of the MMU unit. We have the block layer. We have the scheduler, and yeah, Kmain is also working. EL0 is working, and we also have the interrupts firing, syscalls working. So overall, by adding the file system layer, we should be able to start putting the user processes into the file system and load them directly into memory during runtime, like an actual exe or ELF file, instead of having to hardcode the user process into the kernel ELF. That was the overall idea of the entire file system layer. Yeah, and last week I guess we structured a little bit of the types that we need in general for the VFS layer and also for the X layer. Mm, yeah, let's just continue there probably. Uh, I also need to I forgot to write any to do last week because right now I just checked this file. There's no to dos. No, we are a bit in a blind mode probably. I believe we simply wrote all the types last week. We didn't do anything else. I think so. Yeah, we just went into the actual theory of how X layer is supposed to, the X front end is supposed to keep track of the blocks and inodes, and also how to take the map the first group, first block of the X file system into an in-memory data structure, so we can directly use its fields to access the metadata of the file system that we are working with, or the image that we are working with. I think that is all. Yeah, I think this was that data structure, because currently we have the super block and we have multiple bitmaps and multiple tables, stuff like that. I'm pretty lost at this point because let's see, this is the full idea of what we want to accomplish from the top layer. Whenever a user process tries to, let's say, execute to open bin ls, and we call a syscall that is open, and we handle the syscall, and internally inside the syscall we call the VFS lookup, and the VFS lookup is going to take the input as the file name, file path, the full path, and then we are going to start by finding the root inode. That is currently we also need to figure out which file system this particular file belongs to, because there can be multiple file systems, and we need to know which file system. So we go through the root inode of every file system that are active, and we get the super, and then we look for the initial bin, which is the root directory, and there's the initial inode, and then within that inode we should be able to look up the second inode, which is the ls, and if we found that inode, we can finally create the structure, the file struct with just inode and the offset. I think that's the high level idea of what we wanted to do, and this was written last week. And what is this? User space only passes ft. Yeah, so user space passes a ft, not a file struct. Okay, so yeah, last week we also realized this, that user is not going to user process is not going to pass a actual file. It's only going to pass an integer. An integer is like a which is the ft, file descriptor number, and every process in memory, L1 will hold its own process table with key as the ft number and value as the pointer to the file struct. So if a user process calls ft as 1, when the syscall actually reaches the internal handler, there the handler will just look up the process ft table and use the key as 1, and it will get the respective pointer to the file structure. And within the file structure, we'll know the position of current position and how many bytes we want to read from that position. And then we have to use the actual inode table to get the block. And then this is just extends is the this is how we're gonna represent X file system blocks in front end, because the X front end should also hold some sort of data structure to represent which block that we actually stored the value in the physical layer. So if the x1 is pointing to 0 and the physical block is 0, so its physical block is 4 and the logical block is 0, and there's x2 that can have a physical logical block of 5 and the physical block of 10. And within the x there is also another field, that is the range, how many blocks are covered. So in this case, the actual physical block 456 to 450 is, what the fuck, 456 to 450, probably I meant is 460. So it's like 4 blocks, and here did I mean it as 5 or 10? It only has 5th logical block is pointing to the 10th logical block, and from 10th logical block, no, I fucking forgot. No, I don't understand this block now. Oh, this is why we should write better comments. Every week I go through the same fucking ideas again and again, and it still does not make full sense sometimes. I know it will have the X table information, the number of based on the current index, based on about that. No, we need to understand this. I don't get it. Explain this again. How extends are used to used in the front end to keep track of the physical blocks Okay, because we need to understand it. I guess we will have to write this part of the blocks today. We have almost everything else. So X used indirect blocks, blah blah blah. Mm-hmm. Run of a continuous logical blocks mapped to run a continuous physical block. Okay, so every extent has a extent header and entries within it. Header has these values. We have the magic number and we have the entries, that is the total length, and max. Oh, fuck it. And every value which is the entry is a leaf probably, and leaf block actually has the length and starting and after physical start. And we have a header, so we have header, let's say we have 2 entries and maximum of 4 and depth is 0, so this is the leaf entries. Because depth is 0, if it is 1 then probably we still have to go down the block. And next one is E block, which is 0, which is logical, and length is 5 and E start is 456, so which is the physical block. So it is correct. Yeah, I just have to, so this side is it's not like 0 to 4. What we store is just 0 and we store the count is, let's say 5, in this case is 4. That means starting from the logical address 0 we have 4 contiguous block, and we also have a physical start which is 456. So starting from physical block 456 we have a 4 continuous physical blocks. So this is almost correct. Okay, what else do we have to think about? So in our logical level we just always start from 0, and every logical contiguous extents will map to a physical range. I think that is all. So let's check actual example. So reader wants the byte offset 30,000 of a file and block size is 4 KB. So the target logical block would be 30,000 divided by 4 KB. So we should reach the 7th block, and offset within the block is we divide, we get the remainder of this same operation. So within the 7th block we need to get the 1408 bytes. Now we walk the inode extent, read the magic value, and depth is 0, so it's leaves and entry, there is 2 entries. So we go through each extent, and the first extent says it is block 0 and till length 5. So we check if our target logical block is within that. No, so we go to the next extent. Next extent starts from 5th and it has a total length of 6. So 5 to 11 is and our block is greater than and equal to within this range, so we can go into this extent, and within this extent we take the physical block, which is e start is 600 plus 2, which is just our difference. So we need to read from the 602nd block. And physical block into 4906 plus, and then we can just call block read with the block number and a buffer. That's it. And let's consider that the header has a depth of 1. What does that mean? That means we have to go until we find the actual block. I guess that's it. Nothing much. And but the header block actually has index, not extents. Okay. So at each level we read the node header. If the depth is 0, we scan the extents and find the one. Else we scan the index entries, find the largest block that is less than or equal to our target block, and we try to block read that physical address, and then we start the same thing over again, because within that block probably we'll have the same header there, and we again do the same thing. So next, so if we write the structure in full types with all the fields, we can directly cast the block and then walk the tree if it is depth. Okay, so we also have to not assume that every extent will be within this. Okay. So if we have a header with depth 0 and 3 entries, what's the physical block holds logical block 3? It's 201. And what's the physical block holds the logical number 9? It's 301. And then what should read written when user reads logical block 6? What do you mean if you reach logical block 6, 0, 1 and 2, 0, 1, and then 2, 3, 4. Okay, so currently logical block 6 has no entry. Is that what the question is? The question is what should read written when the user reads the logical block 6? Because as per our extents, logical block 6 does not have an entry here. What does this actually mean? We should not have holes, right? Because every time we actually logical blocks should be continuous. Maybe physical blocks can have holes. Okay, let's see. Man to think. Reposition, rewrite file offsets. Repositions the offset of the file descriptor to arguments offset. Okay, according to the must open the file descriptor, positions the file pointer as follows. Current location, okay. What is the definition of a hole? A hole is defined as a continuous range of bytes in a file, all having value 0, but not all zeros in the files are guaranteed to be represented as holes returned with seek hole. File systems are allowed to expose ranges of zeros with seek hole, but not required to okay, it's not like a must. It's probably you can do it, but it's not a mandatory. Okay, now I get the point. So idea here is that in this example, so it's an optimization technique. So here you see we have a logical thing where we have x1, x2 and x3. x1 is mapping from 0 to 1, and then x2 is mapping from 2 to 5, and then x3 is mapping from 8 to 9, and but 6 and 7 is missing. What happened to 6 and 7? Okay, overall 5, 6, 7 is missing. 2, 3, 4 is 3. 5, 6, 7 is missing. What happened to that hole? Okay, is that even okay to have a hole? I mean, in general, it should not, because logical blocks are supposed to not have any holes and they are supposed to be continuous. But in case if the actual represented data is just zeros, that means we don't actually have to keep that in memory. We can just represent it as a whole, as a hidden construct, so that we can save one extent of metadata. Let's question that. Is the whole just to optimize, just save storing extents for mm, for blocks there are just zeros, like an optimization to save space. I think so, because based on this man example, it looks like that. Actual data blocks on, they don't store zeros at all. Okay. Okay. Literally, we simply don't even store zeros. We just assume that if it is just block of zeros, then you can just say that these two blocks are holes. That means whenever you see certain hole, you can simply return zeros in the runtime. You don't even have to store it. Okay, that's really good. So in case if I have a 100 GB of zeros, can one inode represent it? Store 100 GB of zeros. Then a single inode entry without having any physical block can represent it. Just this whole. Okay, now it's interesting. So we 100 GB zero file on disk. So we have inode, which is let's say some inode number, and it's regular now, and size is the 100 GB, and block is just 0, and we have the actual inode block entry where we have the header, and entries is 0 and maximum 4, and we don't add anything in the X, and the entire 100 GB can be just stored in 256 bytes. I guess I'm gonna use this as the clickbait for my LinkedIn posts this week. How to store 100 GB in just 256 bytes. Yeah, it's really interesting. When it once you understand the fact, it feels obvious, but when I was reading it, I was wondering why. First thing that came to my mind was that I could just probably save extents, because I know that I don't have to store that extent because that's just a zero block. But only after I got the answer from it, I realized I don't even have to store it in disk, because it's just zeros. Whenever I come to this condition, I could just return 0 in the runtime, and I don't even have to bother looking it up in the physical block. So only after we understand it, it feels obvious. Okay. Now let's just go back to our example. Let's also just go through this example once again. If we have no extents, that means we just return for every block, we just return zeros. The size should be of the block size. Hmm. Okay, also this is only a support which is called sparse file, and if it is there or if it is enabled in the file system, then you allocate just one inode with a 256 bytes, and you can actually store 100 GB of file. And it's called sparse file support. Okay. Maybe we can go through these examples to actually see it in action. I don't know if these examples will work in my Mac. I'll have to use it inside some Linux target. But if we use these two options, it's going to actually write zeros into those locations. Actually, this is kind of how we format disks. We simply write zeros, because if you simply remove the inode table of a disk, that means the actual physical blocks are unallocated, but then still the old data is still there, and it could mean we are leaking data. So whenever we actually format something, instead of removing the metadata, we should actually write zeros into those physical blocks so that nothing will be recoverable. Okay. Okay, we learned something new. Let's go back to the two conditions that we need to write today. This is the first condition that we need to write. This is the normal use case where the user wants to read 30,000 bytes of the file with a block size of 4 KB. So we do these calculation and walk the inode extend header. Where will this inode extend header be? User process to this point. Every call don't ask any steps. we also need to just go through entire steps so we can just replicate it in our side. So user process calls reads with a ft and with the buffer and the number of bytes it wants to write. So we call the syscall, which is just this. We already have the syscall and we call it, and we are going to this is just hardware interrupt stuff, that's fine. And we are finally going to call the sysread handler. After we call the sysread handler, we have to actually write the syscall handler, because currently we have, I don't think we have syscall reads. Let's see, do we have it? No, we don't. We have write syscall and kmalloc. We have to add that. Okay, within that syscall, what happens is we look up the structure file for this ft. So we have to add this new block for every. Let's write it down. What the fuck is it? We'll do what to do here. That way we can actually start implementing. We've been going through a lot of theory without any actual action. So add a ft table into for every task, and it should hold key value pairs. As key is the ft index, ft number, and value is the pointer to the file structs. That means this is exactly why it feels normal to have separate open and then we have read, because whenever I write just normal Python code, even normal C code, whenever you have a file, you first open it and then you read it. You don't have direct reads, because if you have a direct reads, that means internally that read has to initially first open the file, because whenever you open the file, what you do is within the files tasks file table, we are initializing a ft with the file structure. So it makes sense. This structure is only accessible from EL0, EL1, so we can allocate it internally. So when the syscall open reaches the handler, it will create the new file struct and put it inside this table. Okay, what else then? That is a lot of fucking stuff. Hopefully we can get through it. What is it? Okay, I got a call. And, and then what do we have? Okay, and then we have within the file structure, we should have the file position. Do we have it? Let's check. We have ft, have file operations. Okay, f position means probably offset. Okay, we do have offset. We have the offset fields for our file structs. Okay, and then what do? We call file operations reeditor with file struct buffer count. What the fuck is count? What the fuck is count? Okay, count is just the how many bytes you want to write. It's just length. Okay, and then offsets. Okay, here at this point we call file operations reeditor with file buff and length and offsets. Okay, and then what do? And whenever we actually open the file, the open instruction would have actually registered this ext file. So the open syscall would have registered the function pointer with the actual file systems front end function. In our case, it would be ext4 file reeditor. Okay, this is the moment VFS hands off to ext4. So at this point VFS is over. Now we get into ext4 functions. Inside ext4, what we do is we take the files inode. Do we have a file structure inode? Yes. Okay, so inside ext4 we read the file inode. Okay, okay, this operation is what is still bothering me, because it says whenever we open it, the VFS inode would have been taken from the ext4 inode bytes. Probably we have to go through the entire flow for open operation first, and then we can go for the read operation. That way it would be a little more go for this. Keep the same flow for open operation. So once we have the open syscall, we should be able to picture it even better, because right now lots of things are being done by open, and those are just used by the read syscall, and open is doing all the heavy lifting. So yeah, let's go back to open operation. I believe almost whatever we wrote so till this point should be the same, because we assumed it as open. Because for ft table, whenever we have a new task, we add this table, we allocate it internally, that's fine. And when we have a syscall open, it creates that file structure and it puts that into the table, and it also sets probably this field to 0. And we also register this pointer to a ext function call. And then this is what the register function call, and inside the okay, now this is what we have to care about. Okay, so syscall opens just open file bin ls with some what is it, permission, and then we call all syscalls and we do all the mapping, and we come into VFS layer. Here we copy path string from user space buffer. Okay, why do we need to copy the string? I think I don't have to do that. Maybe I have to do it, but let's see. I think I am doing it a little bit different. No, even in my case, I would just simply pass the pointer, the character buffers pointer, so that will be in a user space virtual environment. So we will have to write a copy from user kind of helper. From user space helper that can take user space address and user space address and task ID probably, which is the process ID, and it has to internally use the process tasks table. I mean, if we are coming from the user table, user EL0, the particular user process, into EL1, that means TBR0 is already pointing to the user space. So we could simply read that address, because that table entries are already there. But still, maybe as we are in, let's just check if the current TBR 0 matches the task ID. If it does, we can read the address directly. If not, we have to update the TBR. We have to store the current TBR and update it with the task IDs TBR and then get the read um, read the value into a kernel buffer and update the tbr 0 to old value again. This is still not zero copy. If it's zero copy, what we have to do is that we have to figure out we just have to figure out the physical address of the address, user space address, instead of trying to update the tbr and reading the value, which is actually doing a copy. We just get the physical address so that we can just access the physical address from the kernel space instead of having to go through MMU. Okay, I think we'll just stick with actually having the copy. Okay, that is done. And reserve a free okay, that is what we have to do here in this case. It will create a new file structure and it will put it into the table. So let's use the last index. Okay, we also have to do make this operation should be removed if anything below this fails. Okay. Now we start the resolution, we parse the string, we get the roots entry. First of all, what the fuck is root entry? I think that is what I talked about in the last session, where when we actually initialize a file system, which is this operation, not initializing a file, we are initializing a file system. When we actually initialize a file system, we hold a pointer to it, and then we can just go into that file system and get its roots, and then we can do these operations. I think so. And this you are assuming that the roots entry is allocated. How does it? So user must have kernel must have already initiated a file system and stored the pointer somewhere. These are few questions I have. Let's see how it's answered. Is only if we have the full picture of what we want to do, we can actually accomplish something. If not, we'll just be filled with lots of unknown things, and it will be currently, so far, I think this is clear. This is clear. There is nothing in between that we are oblivious of. So we should also be able to add this color. We should have these entries fine. And the next thing is that we also need to know the root entry. That is what I meant. It is definitely the mounting operation that is missing. Yes, exactly. We simply need to mount it before we can actually do anything. I think I wrote about it somewhere. Let's see. Inside kmain. Yes, we want to init the file system first and read the super of the image. Okay, so this is where I actually wrote the to do. Hold the copy of the super block and store it in a super block structure. Read the table and store it in memory. Read the inode table and store it in memory. And then only after that we can call the actual VFS create. Because in this case, the VFS create is internally going to assume that there is an VFS init already initialized, and it probably has this stored somewhere. Somebody mounted the root file system before any path walk ever happened, and the somebody in our case is just the kmain. And whenever we so we call VFS init here, and we store a root entry with null, and we mount the roots, and we have to read the super block, allocate VFS super block, block read GDT, block read inodes. And then finally we can just store root entry as this. After that we can do whatever we want to do. Explain the whole mounting process in full. I think let's just finish the mounting today. Okay, this is done. Yeah, I also want you guys to know that my cloud session has access to the actual kernel, the Linux kernel, so that it can give me more idea of how the actual kernel works instead of just it on its own giving out information. It will always take the source from the Linux kernel, and my Linux kernel is actually running in a different container. It's Docker container. I think I have to start Docker first. Then how the fuck it took that information? Probably it knew. I don't know, but I actually gave it specific informations to actually only use Linux kernel as the source instead of fucking throwing random shit at me. Okay. So mount function is going to return a super block pointer. Inside we'll have the super block root, which is the root entry. Okay. We need a entry struct and a global pointer pointing to mount root. Okay. And then mount converts the block device into a tree that VFS can walk. Before mount a device, it just bytes because we have physical blocks that is just bytes. After mount a VFS super block plus root inode plus root entry together with function. Okay. We have super block and roots, and we have a root entry with inodes. Okay. Currently, we are just going to set root entry to 0, which is null. And then we are gonna call the file system type registration. Before any mount kernel needs to set table mapping. Okay, so every file system type can have its own mount function, and this is overkill. We don't need to do this now. We'll only have one. So we're just going to call mount root with ext4. This is not needed for us because we are not going to do this step. Okay, this is what we are actually going to do. So here we directly call block read. We read the zeroth block into a buffer of 4 KB. And then we cast the buffer plus 1024 bytes as the structure, which is ext superblock, and ext superblock has all these fields. And then we have the superblock info. Okay, let's actually do it, start doing it, because it's getting tiring just to read. Mm. We are not going to directly cast it because we don't want to add every damn field, because there's just too many fields. We're just going to use offsets. We have super block. We also have ext group, which within that we have the super block and the other bitmaps, and we have the group operation, which is ext4 group, and we also have ext4 block. And we can store those informations here. Actually, our super block is directly gonna store those information. Okay, maybe I can add some extra metadata here. Yeah, I don't have the metadata yet, so yeah, I can add that. Do we have it? No, I only have inode metadata. I remember adding something about metadata, that's why I wanted to confirm. Okay. Okay, now we need the offsets for these values. Oh my god, that's a really big, really big one. Mm. Or maybe it's better to just write the ext4 as it is, so we can just map it directly as a struct and use them as fields. But I don't have lots of operations yet, so it will be hard to put that. What do I do? Okay, I think I'm gonna stick with offsets. It's not hard, it should be doable. Mounts ext4, and it should take maybe inputs. No, it's not going to take anything. because currently it's just going to be a static one, and we are going to just call block reads in that. Yes. Okay, first we need to read the block 0, read block 0. So we need block operation. Let's include this. Includes drivers block.h. Okay, and I can read it into a buffer. So I also need char buffer. I also need then MMU. Okay, have MMU. Now I can just call char star buff equal to kmalloc, and I need a size of 4096. What? Okay, I need to. I was like, what the fuck? Okay, now I can actually call the block read operation, and I'm going to call 0th block into buffer, and size is 4096. Wait, 4096 is divisible by 512, right? Because if I try to read anything that is not in that range, it will fuck me up. How do we 512 into 3? 6 then 8. Okay, it is in 512 range, so it's fine. Okay, now I have the block read, and it is going to return some pass or fail bytes and event 64 red. And then you put UR printf. Something went wrong, bro. I don't know. Okay, now we have read the 0th block. Now we need the offsets so that we can read the specific bytes from this buffer. We don't need the first 1024 bytes. We need the rest of it. It's currently we're just checking the things. We can also do that. It's pretty simple. We just use buff of 0 and buff of equal to 0x yeah, and buff of 1 equal to 0x53. If it is not, if this is true, and if it is not true, then again we put UART printf starting magic number did not match. I don't know why. Okay, now we have matched it. We can also check logical map size and stuff like that, but it does not matter. We can go to the next one. This is where we actually need the field numbers. Even here we need the field numbers because to get this we need the offset. To get all of these from that super block we need offsets. My entire structures are not gonna be actual representation of the physical fields. So let's give me the offsets of those fields so I can normally access them and build everything. I think so. It should work. It should work. Let's see. If we get the field numbers, we can just what we have to do is we get the base plus the offset number. That will be the operation. Instead of having fields, we'll have offsets. And we can define them, yeah. What is it? As my X group, X block. Okay, I can define here. Define X for, see, I have the entire okay, this will be the operation. We have the block buffer, the initial 1002 bytes is just not needed, plus the offset as Indian, little Indian. I think that should be good. And everything is U32 value, U32 value. Okay. What the fuck? Okay, the 0th bit, which is actually after the 1024 bytes. Okay. Empty block bytes 104, and then we have X4 inodes count. I mean, if we are going to define everything like this, maybe it's just even easier to just put the values there. Why do I have to complicate it? I don't know, should I go with just defining every structure and just casting it, or should I go with accessing it specifically? I mean, I don't want every field. That was the whole reasoning for me to just have offsets. Okay, fine. Yeah, I'm not going to read every bit. Okay, fine. Inode counts is 0x00, and block counts okay. Inode count is 0, and what else do we need? First of all, why did we come here? Let's go back there and see what we need. We need log block size, inode per group, and feature incountable and yes states. Let's put that. Inodes log block size, and then we have inodes per group, and then we have feature incompat, and then we have states. Okay, these are the 5 fields that we care about in the initial phase, and then we do also care about block size, blocks per group, inode size, total blocks, total inode, roots, number of groups. Oh fucking god. Okay. Block size, blocks per group, and inodes per group. Inodes per group, inode size, and then we have total blocks, total inodes. Total blocks, total inodes. Total inodes. And then we have root nodes. Root I don't know what that means. We'll see. Root INO. And we have number of groups. Okay, that is all we need, at least till this point. Let's first of all read those values. Okay, we have inode counts, which is 0. Log block size, which is I18. And then inodes per group, which is 28. And then we have feature incompat, what that is. It is 5C. And no, feature incompat is 60. Oh fuck me. Okay, and then we have X state, which is 3A. Whenever I'm gonna debug something that is missing here, first of all I need to confirm if the offset is correct, because last time I was once debugging something and ended up just reading it from a different offset, and that was the whole error, and it took like a lot of time out of me. So yeah, Now we have block size. What is log block size and normal block size? Huh. I don't even have a block size here. Block size equals to this value. Probably this needs to be computed. Okay, and blocks per group, which is 20. And then we have inodes per group, which is 28. This is already here, remove it. And we have inode size, which is 58. And then we have total blocks. Why the fuck is total blocks? I have no idea. And total blocks and total inodes. Maybe these things needs to be calculated. Yeah, possible. Inodes per total blocks. I think it's just multiplied between blocks per group and block size. No, blocks per group and number of groups, or no? Okay, let's leave total blocks and total inodes. And then we have root INO. So it's also not here. We have first INO. Maybe that's the root node, root inode. Yeah, possible. We also have volume name. So we can actually match this name to confirm if we are actually matching the proper name too. I see, even here it says you actually just calculate the groups by block count by, you actually calculate it, it's not a location. Okay, we don't need these. What about root INO, which is, I believe, first inode, which is the root inode. Okay, whatever. What about number of groups? I think maybe that is also Okay, I don't have these two information either. Find this. Do we need? I think we need the number of groups actually to divide and get the logical blocks for computation. Hmm. Okay, tomorrow let's start with actually implementing the first logic. Today we only managed to set up a little bit of the offsets, and we also have a small structure, and we also know what to do now because we start by finishing this the initial mounting process, and then we'll come back here and we'll start this entire thing, this entire process, because we also know exactly what are the things we need to do now for accomplishing the open syscall, because only if we finish the open syscall then we can actually do the read syscall. Okay, okay, we'll see. I think we'll start this tomorrow then. It's been already 1 hour 30 minutes. Thank you guys. I'll see you tomorrow.